첫 수업이니까 우선 영어로 진행하겠습니다. 네, okay. So today is our first lecture in the department seminar colloquium. So it is my great pleasure to introduce our esteemed guest, Dr. Chulhong Kim. He is one of the most renowned and the most active imaging research player in the medical imaging field in the last decade. So actually, to briefly introduce his career, he got the PhD program in the Washington University at St. Louis at 2009, right? Yeah, under supervision of the Dr. Li-Hong Wang, who is the pioneer of the photoacoustic imaging, the technologies, and he's currently in the Caltech University, and also he is currently after postdoctoral training, he moved to the SUNY Buffalo between the 2010 and the 2013, and at that place I worked with him within a very short period, and then he moved to the POSTECH on the 2013, and started from his academic career from the POSTECH from the 2010. So he's currently in the professor of the Department of the Electrical Engineering and the Department of Convergence and IT Engineering and the Medical Device Innovation Center, Medical Engineering, and he has a lot of the serving at workplace, and the fellow of the IEEE and the SPI and the Optica, and then also his country leading his own company, the Optical, which is providing the optical imaging, ultrasound and the optical imaging systems. Okay, so he has achieved a very notable academic contribution to the community. His current H index is around 72, and the total citation is higher than 18,000. So, yeah, Dr. Kim will be sharing the insight of the multimodal, the biomedical imaging field, offering the valuable perspective that will surely enrich our understanding. So, please join me in welcoming Dr. Kim. Thank you.
Thank you so much. Yeah, it's my great pleasure to be here in DGIST. Actually, Professor Jae-seok Yu was my first master student when I was a SUNY Buffalo, a doctoral student. Yeah, once I decided to move back to POSTECH, I extremely persuaded him to come to POSTECH together, but he stayed in US for his PhD degree. I think that was a really good decision, though. So now he's my colleague. Not student advisory relationship. It's my colleague. We have a long personal relationship. I'm very happy to be here. So today I'm going to talk about medical imaging tool called photoacoustic ultrasound, these types of imaging modality. But at the same time, I can share my personal experience. At earlier my career, like a scientific career, I put a lot of effort on academia. So I tried to publish good paper. I still want to publish good paper, many papers. But I realized, once I joined the POSTECH, I realized many of scientific paper are not very useful in practical perspective. So, so I try to make some more impact in the society, because our tools, our devices must be used in the clinic, because I'm working on medical imaging. Otherwise, everything just in publishing in the paper. So we try to make more, impact in the society. So we do have a lot of clinical studies going on using the technology. Also, we try to commercialize the technology. Maybe I can share those kind of experience as well. So if you have any questions, you can stop me and ask me some questions. So my background, actually not the ultrasound, my background called tissue optics. So we use the optical light. Basically in this room, there is a room light. These are opticals, right? So if you look at the whole electromagnetic wave spectrum, there are multiple energy band, RF energy band, microwave, terahertz, optical, X-ray, gamma ray. If you look at the history of the imaging, people see structure of the something using their naked eye because they are looking at the optical beam using our naked eye, but people cannot see inside. So the first energy band electromagnetic wave people used to see the inside of body, that's the X-ray, right? That's the first medical imaging tool. Then, over the last more than 100 years, technology is extremely well developed. So, but my case is, for my master PhD study, my advisor is actually expert in tissue optics, how light and tissue interact. So why we need to use the optical method? He thinks we don't use any harmful radiation because basically it's the non-ionizing radiation. And then there is optical spectrum. Spectrum means, if you use a room light, which is a white light, if you distinguish different wavelengths from this room light, you can distinguish red, blue, green, purple, different colors of the light. We call it spectrum. Laser spectroscopy has been used for physics and chemistry or biology for a long time. Optical method has a beneficial if you use the optical spectrum, different wavelengths of the light, because different wavelengths of light interact with the tissue differently. If you look at the CT, computed tomography, they don't really provide much functional information because tuning the X-ray spectrum is difficult. So, it's kind of monochromatic, kind of, single wavelength imaging people do in X-ray field, not the multiple energy band. So, spectroscopy using visible or near infrared optical ranges is extremely useful. And then when light interacts with the tissue, any metals, any electromagnetic wave, when they interact with the matter, they either absorb, scatters. In optics, there is a polarization. So this is a fundamental property. If you learn electromagnetic wave, when they interact with the materials, either absorbed, either scatters. That's the main properties. So in optical domain, if you optical light absorbed by the tissue, we can see oxy and deoxyhemoglobin. This basically is the blood in the body. And also melanin, water, lipid, these types of contrast we can get from optical method. And then using this kind of information, what kind of physiological information we can provide? One thing we call the hemoglobin concentration. That's actually basically related to how much hemoglobin in the blood. That's related called angiogenesis. Angiogenesis meaning the forming the new blood vessel, which is widely happening in tumor area or other diseased area. Also, we can measure the hemoglobin oxygen saturation. That's related to hypermetabolism. Any area has more metabolism, there is more oxygen. You can calculate oxygen information using optical method. Also, you may heard about Doppler. If you use the Doppler effect, you can measure the blood flow like ultrasound. Also, we can inject some agent from the outside to do molecular imaging to specifically target some disease. It's called integrin receptor targeting reportogens. There are so many advantages of using optical method. Okay, optical method provide a lot of Nobel Prize in physiology, in physics, in medicine as well. And also it make a huge impact in biological research, even in medicine. But however, if you go to the hospital, many biologists or fundamental scientists, they use optical method to see the biological phenomena. But once people move to the hospital, medical doctors don't use many of the optical method. They use a CT and MRI to see the inside of body, or PET, positron emission tomography, or ultrasound is widely used. Not many optical method. But if you're working in the biology lab, you use confocal microscope, 2-photon microscope, and then show the beautiful images. But once you go to the hospital, you don't see that many optical methods. Right? What is the problem? So this is exactly the problem. So if you drive in the highway without any fog, you can see very far. right? However, under the foggy environment, this is the worst case for driving, the most dangerous. You don't see anything. Although you turn on the light so strongly, still you cannot see anything because it's not matters of the energy issue because, light can traverse in the air, but all these small water droplets in the foggy environment, they deflect that, they scatter the light. It's a completely diffusive. So that's what you can see. You don't see anything under the foggy environment. That's the problem because foggy environment is exactly the same as our body. Our body completely diffuse light like in the fog, water droplet. Why X-ray is so popular? X-ray penetrate through the body, there are some scattering, but not much. Basically, it penetrates through the body. But if you use optical method, every 1 millimeter, they scatters everywhere. So basically, maximum penetration depth of the all optical method for biological application, theoretically, that's the 1 millimeter. Up to the 1 millimeter, they can travel without any scattering, but beyond the 1 millimeter is completely. So basically, you cannot, track the photon in the biological tissue. So that's the problem, which means, although there are so many advantages to use optical method for biology and medicine, eventually, since it cannot penetrate deeper in the tissue, it's not widely used in the clinic. That's the key problem. So, in my lab, when I start my, graduate study, we want to provide optical contrast, which is good because there are reach of the contrast. However, penetration depth is limited, so we need to improve the penetration depth. That's the goal. So we use called the photoacoustic technology to break, this fundamental problem in optics, in tissue optics. So we want to provide strong optical contrast, optical information, but we want to provide deeper, and then we want to maintain the resolution. So what is a photoacoustic? So it's not, new phenomena. We can see this phenomena in our daily life. So in heavy rainy day, you sometimes see the lightning, right? What happened after the lightning? Students, if there is a heavy rain, there is a lightning, what happened after the lightning? Yeah, thunders, right? Lightning is a light, right? Thunder is a sound. Thunder never comes before the lightning. You see the lightning first, and then after that you hear the thunder. There is some time difference. Why there is a time difference? Sound wave need to propagate in the media. It requires time. That's why when you see the lightning, after a few seconds, you hear the thunder. There's a time difference is there. So this is a photoacoustic effect. So we see this one in our daily life. People didn't know about this, but, along the all human beings' entire histories, we see this phenomenon. But, there's a person, his name is Alexander Graham Bell. He actually brought up this idea to scientific society. There is a photoacoustic phenomena. So he proved it. So why he started looking at this kind of phenomena? But Alexander Graham Bell is the guy who invented the phone, right? He was, I think, like Elon Musk, but in 150 years ago. Why? Because when he discovered the phone and then he invented the phone, he started the business. The phone device is not expensive, but he realized, cable between two locations are becoming more expensive. That's why he thought about, only near distance communication they perform, long time ago. Nowadays people do long distance communications. But he thought about at that moment, already wireless communications. Without using the cable, if you can communicate to each other, that's the completely changing the, entire business area at that time. So what he did, he used the light, and then he convert the light to the sound. Initially, what he thought, if he can convert the sound to the light, and then send some light information from one location to the other location, without using the cable, and then also reconvert, light to the sound, and then we can do wireless communications, right? That's what he discovered. He realized, light can generate the sound at that time. He did experiment. Then he published paper in Science. He called photophone. He named the called photophone 150 years ago already. All right. Then, this technology been there for a long time, but, no one really looked at this technology until 1980, 1990. Laser technology become, better. Electronical technology, electronics becoming better. So, all this coming together, and the people looking at this technology in medicine from early 2000. So, if you look at the conventional optical method, excitation is the light, emission or detection of the signal also light. If you look at the conventional ultrasound, we transmit the acoustic wave and receive the reflected acoustic wave. In photoacoustic, we don't send ultrasound. Instead, we use the pulse laser. It's like a lightning. We generate the lightning on the human biological tissue. But we use a pulse laser. It's like we use the same laser as dermatologists use. It's already these types of lasers being used in the clinics. So we use a very short pulse of the laser. It's like lightning, but there is a light absorption and heat generate. It's like if I wear the black t-shirts, you go outside in sunny day, what happens? Your black t-shirts absorb the light, right? Your body temperature increase. So exactly the same thing. Some target has the color that absorb the light at specific wavelengths. And then there is a heating generated. We are not talking about several degrees of temperature rise. We are talking about millikelvin, very tiny temperature rise. And then there's called thermoelastic expansion. Any elastic material, if there is a temperature rise, they are expanding. It's like a balloon. If you look at the balloon, if you increase the temperature around the balloon, what happens? Balloon is expanding, right? So since we are using pulse laser, it's expanding and shrink, expanding and shrink. That basically disturbing the medium, and then acoustic wave propagate. So 1 millikelvin temperature rise is equivalent to the 800 Pascal. That's strong enough detected by conventional ultrasound transducer. This is why how light and sound, how light converted to the sound. So this is the only equation I have in this slide. It's a very simple, first order equation. So pressure amplitude is proportional to the multiplication of these 4 parameters. If you look at from the last, it's called F. F means optical fluence, which means if you dump a lot of light, you can get strong acoustic signal. So you can use very strong light. You can get strong signal. Very simple way. It's a linear relationship. However, this one controlled by safety limit. You cannot use such a high energy of the light. You can damage the tissue. So it's controlled by safety. This is important. Optical absorption coefficient. So any electromagnetic wave I said, when they interact with the tissue, they either absorb or either scatters. How much absorbed, how much scattered? That's called absorption coefficient of that particular material or scattering coefficient of that particular material. Any specific material, they absorb the light by, controlled by this coefficient. This is only predetermined. But this one interesting parameter. That's what your eyes are looking at. When you look at the black color, black color absorb the light at certain wavelengths. Your eyes is sensitive to this. This how much black, extremely black, lightly black. There is a concentration difference. It determined by this coefficient. So this one is a wavelength dependent. This one is concentration dependent. So that's why we can look at the mu A called optical absorption coefficient. That's important. And then sigma called heat conversion efficiency. Any material when they receive the light, in quantum physics, molecule need to excited from ground state to the excited state. Anytime if you receive the energy from outside, then they must release the energy. Since they get some energy from outside, they must release the energy. One way to release the energy is emitting another wavelength of light they called fluorescence. They emit another color of the light, or the other way, energy converted to heat. That's why we detect. It's called heat conversion efficiency. You may heard about fluorescence, right? Like there is a fluorescence sticker. You put on the ceiling, you know, if you turn on the light, you can see fluorescence light is coming from the stickers, right? You touch that sticker, it's not, you know, you don't feel any, you know, heat there because, you know, energy converted to the fluorescence. And the first one is called local temperature. We can measure the temperature. It is local, you know, measuring body temperature is easy. You use the thermometer to just measure the global body temperature. But we are not talking about global body temperature. We are talking about local body temperature. Let's say I want to measure the temperature on my liver. I want to measure the temperature of my breast, whatever. Localized temperature, measuring localized temperature is difficult. Now, only MR can provide magnetic resonance imaging called MR thermometry. They can provide the temperature information. But if you detect this signal, you can also map you know, temperature information in the body. Then light converts you to the sound. Then sound is generated in the medium. They propagate through the medium, and then they detected by the transducers. So the other way to detection part is similar to the regular ultrasound transducer. Ultrasound imaging. Interestingly, speed of the light is 3 times 10 to the 8 meter per second. Speed of sound is only 1500 meter per second. So speed of light is too fast, so you cannot catch the light. But speed of sound is too slow, you can catch it. So you can basically provide called time resolved signal. Time resolved signal means you can distinguish, you know, sound wave at different time scale. This time scale eventually convert you to the distance. That's why you can measure the distance from your side to the original signal origin. So then, you know, we can form the images. So that's the principle. And what kind of, you know, information we can get from the body? So this is optical spectrum. So that's why we are looking at visible, or if you go slightly more, it's called near infrared window 1. Now in this wavelengths in our body, hemoglobin absorbed a lot of light. So basically blood absorbed a lot of light. So if you open the body, what you can see in our body, you can see the blood color. Red color for artery, blue color for the vein. If you go shorter wavelengths, it's called the ultraviolet light. You know, ultraviolet is very sensitive to the DNA and RNA and protein. Protein, DNA and RNA absorb the light a lot. You know, this basically in the whole of the cell nuclei. So if you use these wavelengths, you can see cell nuclear information. If you go slightly further, you can inject some contrast agent. Many chemists make material science, they made contrast agent, can images. If you go beyond more, you know, collagen, lipid, they absorb the light, and then we can images. So through this contrast, you know, we can provide, as I said in the first slide, angiogenesis. It's a forming new blood vessel we can monitor. And also we can see oxygen information from diseased area. Also we can provide some morphological, like a blood vessel distance. Blood vessel called tortuosity. They're, you know, they're moving around. Now how tortuous there we can provide. Also we can provide molecular information based on the contrast agent. So these are what we achieved over the last several years in POSTECH. We developed called super resolution photoactivate atomic force microscope and also near field scanning photoacoustic microscope. This is kind of microscopy system widely used in fundamental science like physics and chemistry. So we developed microscopy. This is very similar to the confocal microscope. We call the optical resolution microscope. And also we developed called intravascular photoacoustic ultrasound catheter. So ultrasound is widely used for, intravascular means we put the sensor into the blood vessels and to image the coronary artery disease. That's widely used in ultrasound. We add a photoacoustic part. Also, ultrasound is widely used in endoscopy perspective, like a stomach endoscope, you know, intestinal endoscope. That's what we can do. Then if you go a little bit bigger size of the scale, we've developed, you know, whole body small animal imaging scanner, like a micro MRI, micro CT, micro ultrasound, micro PET. You may heard about small animal imaging scanner, you know, for the entire body of the small animal we developed. Finally, we developed clinical machine. I used to work with the Philips, Alpinion, Samsung Medicine, and we initiate our own company to commercialize this. So finally, I work with the Professor Jae-seok Yu about ultra-fast Doppler imaging. It's like a new generation of the ultrasound imaging. So these are some examples. So these are first version of the microscopy. So I want to move to every single system we develop. We want to introduce. So as I said, this is kind of called confocal microscope, widely used in biology. So using photoacoustic method, we developed the microscopy system. As I said, blood absorbed a lot of light. So we can see this blood vessel information without any inject contrast agent. So which is good. If you use a CT, you need to inject the contrast agent to X-ray angiography. For MRI, you need to inject some contrast agent. But this one without any inject, so we can see nice blood vessel imaging from small animal. This is a mice imaging, ear, and then these are brain cortex, brain blood vessel imaging. Also, we see the blood vessel from the eye, and this also eye. These are all 3D images we can render in 3D. So this technology already been commercialized by the company in America called microphotoacoustic more than 10 years ago. But it's not popular. Not many biologists are using this system. So what is the problem? Although it can provide a very nice imaging, the problem, they are extremely slow. So it takes about 30 minutes, sometimes 1 hour to acquire these images. So that's why we try to speed up everything we want to image quickly. So that's why we made the imaging systems in our company. 2 by 2 millimeter, we image for 2 seconds. Previously, it took about 30 minutes or 1 hour to acquire imaging. So 6 millimeter by 6 millimeter, within few seconds, we can provide images. So also we can provide all kinds of software like a zoom in, zoom out, like a vessel size and vessel density, and we can provide. Also, we develop our own software for 3D rendering. It's all real time in MATLAB environment, using the CUDA, and then we can provide all 3D rendering software. I know many imaging people, students, need to process the imaging in 3D and then make a movie, but the software is very expensive. Sometimes students use the cracked version to use the commercialized software, but we made everything in MATLAB environment in real-time process. So this is a microscopy system we developed. So using the system, we do some small animal studies. So we monitor vasoconstriction. Vasoconstriction means the shrink of the blood vessels due to the acute hyperglycemia. If glucose level is suddenly increased in bloodstream, blood vessel diameter can be shrink. So we increased glucose level in the bloodstream from 140, that's the regular cases, and it become more. And then we image the same animals for, in time series manner. And you can see, we can quantify change in glucose level, which is in the black, and then change in arterial diameter, which is in red. So as you can see, suddenly glucose level is increased, arterial diameter is suddenly decreased. Once they go to the steady state, and arterial diameter is, go to the steady state. So change in glucose level is matters, actually, can change blood vessel diameters. The blood vessel is shrinking and expanding. Second one, we develop even further systems, like a B-mode imaging system called how much cross-sectional image you can provide in terms of the speed. Previously, we have about 100 to 200 hertz of the B-mode imaging, but maximum we can achieve 500 hertz imaging speed. Then, we can see flow of the RBC in the bloodstream. So we can provide blood flow information in small animals. Also, there is called localization technology. If your imaging speed is so fast, and also if your signal to noise ratio is so good, you can localize the signal, and then you can improve the spatial resolution even better. It's called the super resolution imaging. I don't know you may heard about this technology. In fluorescence microscopy, people introduced this super resolution technology, and they received the Nobel Prize, I think it's 2014 in chemistry. So we use the same localization method in photoacoustic, and we improve the spatial resolution beyond the hardware limitation. So maybe I can skip here. Now we can image the humans. Initially we block the blood flow in the arm, and then we look at the blood vessel information in the finger. This is a cross-sectional image. Basically, we see the cross-sectional blood vessel imaging in the finger. So initially, not many blood vessels are showing because we block the blood flow. And then once we remove this perfusion, you can see new blood vessels start coming. So basically, blood vessel density we can quantify over the time. So you can see these are all 3D information you can render in 3D. Also, we can see in the change in oxygen in the bloodstream, because red means higher oxygen, blue means lower. Artery is red, vein is blue. Changing the oxygen is extremely important in the bloodstream, so we can monitor in the human finger over the time period. Also, we can extend the field of view, so we can see blood vessel of the entire human palm. So this is amplitude, this is depth. So some people are very interested in this technology in terms of security purpose, because previously people used image the fingerprint to see for the security purpose, right? Now people want to see blood vessel network as a security purpose. All right, these are the blood vessel imaging. Now I move to the more clinical side. So it's called histology. Histology means in the pathology department in the hospital. So pathology, what typically happens during the surgery, if there is a cancer, surgeon take out small portion of tissue in the operating room, and during the surgery, they send this tissue to the pathology room. So tissue go to the pathology room, 병리학실. Pathology room is right above or right below the surgical room if you go to the hospital. It's right there. And then once they receive the sample, initially they freeze and they section and they stain. Pathologists, they look at the tissue, whether there is a cancerous cells or not. If there is a cancerous cell, they call to the surgery room, okay, you need to come more. So because it's margin, looking at the cancer margin is important, so they take out more and more and more. This process is repeatedly happening in the pathology. So I think if you are working on biomedical, you need to go to the hospital, how this process is going on. In the pathology room, I can definitely say they already put a piece of papers there, freezing only 1 minute, let's say sectioning 2 minutes. They specified each process of time. Why? Time is very important in pathology. So if you use our technology, we don't need to freeze because we can provide 3D information. So we don't need to section. We don't need to cut the tissue. Also, we don't need to staining, because if you use ultraviolet light, we can directly image the cell nuclei. So why people are doing H&E, they look at the structure of the cell nuclei. So without any staining, we can do. So all these processes completely in one-stop process we can do using our technology. So we image the human colon cancer, but we take out tissue from human colon cancer, but we did not treat anything. This is unprocessed tissue. Top one, we acquire imaging using our modality. Bottom one is conventional microscopy technique, with pathologists to use. So we can see non-cancerous area, cancerous area, and the boundary very clearly. So they very well match each other. But qualitatively, image looks like very similar. But once you see in detail, quantitatively, our image quality is even worse than the conventional, because this is hardware limitation you cannot overcome, because you need to do beyond conventional hardware system. But pathologists in the hospital, most conservative people, they are really picky. They said, oh, details, your detail and conventional details are different. So that's why we apply the deep learning technology. Deep learning is extremely powerful in pathology. So what we do, initially we acquire the grayscale imaging, but next one we call the virtual staining. We're using the deep learning, we change the color, but our deep learning result is very similar to the conventional histology, is called virtual staining. Once we did the virtual staining, we apply the segmentation. Basically, we can make a boundary of each cells. Since we're making the boundary of each cell using the deep learning segmentation, we can quantify some quantitative information. Then finally, we apply the classification, whether it's cancerous tissue, whether it's not cancerous tissue. So virtual staining, segmentation, and classification is a one-step process we applied, and our result is very similar to the pathology interpretation. So now we want to move to this technology in the clinic. That's what we are doing right now. All right, this is some technical development. So previously, we are working on photoacoustic when we need to combine light and sound together. Now, since we need to combine these two devices together, is difficult because people use a lot of tricks. Like this is a light excitation source, ultrasound detector. If you want to put two devices into the one small size, it's difficult. There is some design expert to need to design. So why this problem is coming? In ultrasound, they use ultrasound transducer. Ultrasound transducer, one device transmit ultrasound and receive the signal. In optical side, that's called objective lens. Objective lens transmit the light and receive the emitted light. In photoacoustic, excitation part is optical method. Detection side is ultrasound transducer. Now, making two devices complicate in small form factor is difficult. So what we do, conventional ultrasound transducer has the color, opaque color, so light cannot penetrate. But we develop new transducer called transparent ultrasound transducer. So using that transducer, since it's a transparent, light can penetrate through. So we can use this as the optical window. Then everything become very simple. We can make everything in small size. So this was what we early developed in 2021. We use this transparent transducer. We actually combine the 4 image modality together. Photoacoustic, ultrasound, OCT is called optical coherence tomography, another optical imaging method, and fluorescence, 4 imaging modality together. So this is our photoacoustic part. This is a regular ultrasound. This is OCT. This is a fluorescence. So we image the chemically injured small animal's eye. So we apply the chemical, and then we make the injury. So before injury, we can see blood vessel from the small animal's eye, and after that, you see this red blood vessel. These are called cornea neovascularization. Because of injury, there are new blood vessels are coming. It's called cornea neovascularization. And also in OCT and ultrasound, we can provide cross-sectional imaging. Basically, we can provide the structure of the eye. So for example, thickness of the cornea is related to inflammations of the eye. So we can provide from OCT. But the other ultrasound can go deeper, and we can see deeper structure. Fluorescence, we actually apply the fluorescein dye, and then green area where inflammation area is there. So that's what we did. Then we can quantify some information there. But once we develop this transparent ultrasound transducer, everything is good. The problem, the quality of transducer is not good. It's very sensitive to receive the ultrasound, but it's not sensitive to transmit the ultrasound. Because typically, regular ultrasound, there is a piezoelectric material. There are many transparent piezoelectric materials. But there is a backing, front matching and backing matching material. If they properly used, we can boost our transducer performance. But at that time, we are only focused on to make the transducer which is sensitive to the receiving side. But the structure is very simple. But once we go, transmit efficiently, it's typical. So we make the transparent front matching layer, transparent backing matching layer. Every layer need to connect each other. We use a transparent adhesive. So everything is transparent, but performance is same as commercial ultrasound transducers. That's why we develop, although it's a transparent, efficiently send ultrasound, efficiently receive the ultrasound. So that's why we develop new transducer, highly sensitive. And then, we image the small animals. We can improve the penetration depths. Now we can improve. So previously only, we can penetrate a couple of millimeters. Now it looks like, we can go further. We can see some internal structure of the small animals. Now we are working on the beauty of this technology. If you can make an endoscopy or a catheter small size, that's even better because structure itself is very simple. We use optical guideline. We just put the transparent ultrasound transducer in front of the prism. Then everything is very simple because many people working on endoscopy using this technology. But the problem, since they need to put optical excitation source and acoustic detector in small size, the efficiency is no good. They lose the performance in optical. They lose the performance in ultrasound. But however, if you use technology in the clinic, you need to maintain each technology's performance like 100%. So that's why we use transparent transducer. It's very sensitive, and then we make the endoscopy about 2.3 millimeters. So this size of the probe is perfectly matched to, commercial Olympus endoscopy system instrumentation channel. We inserted, we image the, pig's stomach. So we can see pig stomach, color showed photoacoustic, gray showed ultrasound. This is interesting. The more important thing, we see every single layer in the stomach. Our ultrasound image quality is a very similar, or sometimes is better than conventional Olympus endoscopy system. So since ultrasound image performance is good, now GI tract specialists, endoscopy specialists, they are looking at our images, right? Because the ultrasound image is so good. Then also we can provide some blood vessel information through the photoacoustics. Right, maybe I can skip a little bit. These are all 3D, we can render in 3D. So now I can move to the whole body imaging scanner. So previously system is cheap because we use only single element transducer. If you pay more money, like if you use more element of the transducer, you can provide a better image quality. Also we can use, high data acquisition systems. So we use a 1024 channel ultrasound element, which is a ball shape, and then we use 256 data acquisition systems. So these are the whole body imaging scanner. We see from head to the tail. We put the animal in ventral and dorsal and sagittal view. The color show the depth. This is like we can see major organs, major blood vessels from small animal. But these are all 3D structures, so we can render in 3D, like we can provide slice information like a CT. In dorsal view, you can see spinal cord. You can see liver, intestine. Here you can see the kidney. If you go deeper, you can see the heart and then the lung. So also we can see some dynamics. We inject ICG called indocyanine green dye. This is a before injection. Once after injection, your blood vessel signal is increased. You can see signal enhancement in the liver and all this intestine. You only focus on the kidney area. This is a before injection. Now contrast agent flow in. You see the flow in and the signal increase in the intestinal area. This kidney and the liver. So also we can see the brain structure without opening the skull. Red means is higher oxygen, blue means is lower oxygen. We can monitor brain activation. It's like what MRI does. Also, we can see some dynamics of the heart. So recently, we studied this one for tumor study. So many people use subcutaneous tumor model. We inject the tumor cell when we monitor how tumor is growing. Over the time period, we monitor single animals. We don't need to sacrifice. So we can quantify blood vessel density, and blood vessel tortuosity. So, and then we can quantify hemoglobin oxygen saturation. Since we can measure the oxygen, over the time period, we can measure the oxygen. As oxygen becomes lower and lower in the tumor area. That's called the tumor hypoxia. The tumorous area as oxygen is low. Also, we can inject contrast agent. In this case, we inject the micelle form of the IR dye 780. That's the fluorescence dye we injected over the time period that's accumulated in the tumors. So these are typical biology study does. But we extend our technology to metastatic tumor. We spontaneously generate the tumor in the liver area to generate the metastatic tumor. So at day 0, you don't see any tumors there. So the color shows the hemoglobin oxygen saturation. As time goes by, you can see black dots are coming and become more blue and blue. That's our metastatic tumor in the liver area. So this is a 3D structural movies to show where metastatic tumor is. Also, we inject contrast agent. So this micelle form of contrast agent, before injection, we don't know where metastatic tumor is. But after injection of the 12 hours, you can see some signals pops up. They're metastatic tumors. So looking at the metastatic tumor is important because that's actually changing the treatment outcome of the tumor cancer patient. Then maybe I can skip here. Now I can move on to the clinical systems. So these are the ultrasonic machines you see in the clinic. It's widely used. So many people ask me whether we can use conventional ultrasonic machine in the hospital for photoacoustic imaging. Our answer is no, we cannot use it because the conventional ultrasonic machine is always designed for transmit ultrasound and receive the echo signal. All this beamforming based on round trip of the ultrasound. So somehow we need to change this one. So there are few imaging systems, we can do these types of work. That's what I work with the Philips. 15 years ago, Philips have these types of system. Samsung Medicine had one, and Alpinium Medical, and then our company, we made our program of ultrasonic machine. So and then we put the portable lasers. First of all, we are interested in imaging human foot because there are blood vessels in the human foot. Blood flow in the human foot is highly related to the diabetes. So this is an early experiment. This is the system, ultrasound machine, laser machine. We made a water tank. We put the humans foot in the water, and initially we acquired the ultrasound, and then after that we shine the laser, and then you can see gray shadow ultrasound, color shadow photoacoustics. So we acquired two images, we multiply acquired the slice, and then we form the 3D. So we provide the 3D blood vessel information, the high resolution blood vessel information without any inject contrast agent. So that's what we are working on in our company, heavily working on the peripheral angiogram for photoacoustic imaging. Also ultrasound, we image any part of the body using handheld scanner. So previously foot specific system, now is a handheld system, we can image any part. So gray shadow ultrasound, color shadow photoacoustics. So these are one example, we image the human thyroid. So human thyroid imaging, ultrasound is gold standard. So they never miss the thyroid cancers. Now why? Because this is ultrasound, there is a thyroid nodule. When endocrinologists, they look at the thyroid nodule, based on the shape, based on the size, they can make a score called thyroid score or ATA score. That score between 1 to 5, 1 means benign, 5 means malignant. So definitely 1, no problem. Definitely 5, no problem. Always problem coming to 3 and 4. So they, endocrinologists, they don't know whether it's malignant, whether it's a benign. If that's the case, what endocrinologist does, they always say the malignant. Why? They cannot, if they miss the cancer, that causes a lot of problem. Since everything is malignant, everything is malignant, they never miss the cancers. Because once they say the malignant, they go to the biopsy. Once they go to the biopsy, although it's not malignant, that's okay. They, confirm with the biopsy. But if they said benign, but it turns out malignant, that's the problem. So that's why it's called the sensitivity. Using the ultrasound for thyroid cancer, sensitivity is almost 100%. They never miss it because they always said malignant. But specificity is extremely low. Why? Because they said malignant, however, that's not the malignant. So they need to perform the biopsy. Biopsy is expensive. In South Korea, in China, Asian country, biopsy is cheap. In America, in a European country, Western country, biopsy is expensive. More biopsy, more medical cost, medical cost is increased. They need to reduce the medical cost. That's related to insurance. So if you want to working on biomedical stuff, you need to know how this medical problem going on. So it's not imaging of the thyroid. It's not saving the patient. It's basically reducing the medical cost. It's the same problem in breast cancer. Breast cancer sensitivity using the ultrasound is close to 100%. They never miss the breast cancer in ultrasound. However, specificity is extremely low. So they need to pay more money. So it's the same thing, but we add a photoacoustic there, maintain the sensitivity, but we want to improve the specificity. So we make a new score called ATAP. ATA means American Thyroid Association guideline. That's what ultrasound score, multiply by photoacoustic probability, we give the new score. If this number is above the 0.5, we can suggest fine needle aspiration biopsy. So previously, ultrasound alone, the specificity only 17%, but improved to the 55% using our technology. So one company in America called Sino Medical, they received FDA approved for breast cancer by improving the specificity. Recently, they get the insurance code, which means people use this technology and then covered by the insurance, which that's the world first in breast cancers. Also, we can image the human melanoma. Because melanoma is a pigment, we can clearly see the boundary. And also we can see other part of the body, and we can see the neck. Neck is important because we're interested in the leg imaging also. Finally, we just briefly introduced. This is another technology called ultra-fast ultrasound Doppler imaging. The regular ultrasound, they only, in order to provide Doppler information, they provide about 80 frames per second. But if you get more than 1,000 frames, although image itself, you cannot distinguish structures, there is a small differences in the images. So once you find that small difference, basically you can provide much higher resolution. This is basically localization kind of technology. It's very similar. They're called the ultra-fast Doppler. So that's why we image the red kidney, small red kidney. These are regular ultrasound image. You don't see any blood vessel information clearly from B mode. However, if you apply the ultra-fast Doppler image processing, you can convert that imaging in order to see the nice blood vessels. Because blood flow change in the ultrasound imaging qualities. So that's why we applied. So we can see tiny structures here. Also, more interesting, recently we work with Professor Jae-seok Yu at DGIST, and then we apply this technology for the human study. There's our regular B-mode ultrasound, but we apply the ultra-fast Doppler imaging concept in order to see the human. These are blood vessels from human. You see very tiny structure of the blood vessel from human kidney. And then if you applied another technology, we can go deeper. So you can improve the imaging penetration depths. So, we image the 3 types of patients called normal and the CKD number 3, CKD, chronic kidney disease, 5 with a different patient. And we can see how much blood vessel, blood flow information in the human kidneys. So these are final slides. So this is our ultrasonic machine, and we developed from our company, and then there are 2 wavelengths optical laser source, and then currently we are doing Korean FDA approval process. So maybe I can show some video. This is ultrasonic machine and laser machine. There is a touch panels here and a few buttons in the screen. There is a regular ultrasound and the photoacoustic in B mode. You can see directly. So we put the 3D scanner, we can put into the human foot. And then there is a foot panel for the laser safety. Once you put the foot panel, and then you can see ultrasound and the optoacoustic signal together, and then scanner is moving, and we can see blood vessel information around the human foot. Then later, we can provide some oxygen saturation information there. All right, that's what I prepared for today's presentation. Thank you so much.
Okay, thanks for a great talk. And do you have any questions? Any questions? No more questions? Anyone?
Thank you, Professor, for the nice talk. You show me the whole body image of the mouse.
Yes.
With the 3D scanning, right?
Yes.
I just wonder, in the image, it didn't include the brain. So I believe you can also include the brain at the same time, right?
We can image the brain. Yes.
Including the whole body.
Yes.
Brain.
It's a whole body scanner. Yes.
And I would like to know what will be the scanning time,
Okay.
and what will be minimum resolution you can see,
Okay.
and how long it takes to scan the body.
Right. So like so there are few imaging mode. So the way I show here, maybe I just skip because there are too many details there. Oops. So these are, we just position the animal. Scanner is moving from the below. It takes about, I think it's about 1 or 2 minutes to acquire whole body imaging. But animals is laying down. We image from the bottom. But we have another approach here. Animal is hanging like this, and then scanner is from the side. So and the scanner is rotating like a CT. One slide, one area, one position here, it takes about 9 seconds to see. The entire body, I think, less than a minute. I think it's 45 seconds something. So because there's a scanner is moving up and down to see the entire. It's like a CT and MRI imaging,
The holder may block the imaging?
No, the scanner is moving. Scanner is moving. Holder animal is actually hanging there. The holder is not a problem.
Maybe through the mouse?
Yes, through the mouse. Yes, there is a little bit of the engineering tricks there because we need to supply the gas to make them sleep.
Yeah.
So and then the nose is in the not water, but the other side of the body is in the water actually.
The animal is still, it's not kind of shaky.
It's not shake that much. Yeah, because our imaging is quickly. It's one layer only 9 seconds. So
Then what could be the minimum resolution?
minimum resolution is around I think 200 and 300 micron.
Fine.
Yes.
Thank you.
Yeah.
Any other question? Okay.
Yes.
For your talk, although you showed lots of fascinating imaging your device, but I barely could find the brain imaging as well.
Right.
So how do you think? Do you think your photo-acoustic imaging can replace the functional MRI or the
So that's difficult question. Is no technology replaces the other one, but they can coexist each other. I think. In some sense, blood vessel imaging and hemodynamics, photoacoustic has advantages. But certainly the structural information or molecular sensitivity, the PET is, you cannot beat with a PET. PET molecular information sensitivity is extremely good, right? So you need to. This is a multimodal imaging perspective, right? That's why we actually try to use technology in similar way. So some group in Switzerland or this group, they are actually combining photoacoustic, ultrasound, MRI together to get different information. So also we are doing similar work at POSTECH. So I think complementary information can go. But for brain imaging, nowadays many people are doing calcium imaging also. The brain activity, people doing live awake animal studies using photoacoustic. That's our problem. We don't do that much, but there are many people are working on this. But simply, the main reason we are not doing because we don't find the proper collaborator. That's what we are not doing. But if you can find the proper collaborator, we can do it. Yeah.
I'm very interested in the calcium imaging.
Yes.
Versus imaging.
Right. So you need to use some different types of contrast agents.
Right. We have a chance to use your transparent.
Right.
Translucent.
Right.
It may be ultimately available.
Right. So actually, I talked to many the fluorescence guys. So fluorescence guys need to use this transparent transducer. We're gonna combine with a 2-photon microscope, confocal microscope. Even using this transparent transducer, we can activate the brain using the ultrasound. There are so many work can do, but we cannot find the proper collaborator.
Okay, is there any other questions? Okay, my last question is there any ongoing clinical trial of the particular imaging other than the microvasculature on foot or the endoscopy?
Endoscopy, we image the pig. No, so it's getting, it's called IRB approval. So, if you have any issue about IRB, you should ask me. I deal with so many hospitals in South Korea, any universities. IRB is the problem. So, we do human foot imaging in Seoul St. Mary's Hospital. And then we do carotid artery imaging with the Yeongnam University in Daegu. So Yeongnam University in Daegu, they actually help us a lot. We imaged about 150 patients already. So somehow we are summarizing our result now. So maybe you can report in few months. So carotid artery imaging, we imaged 150 patients. Also another types of foot imaging, but that's not regular foot imaging. We also do at Yeongnam University's School of Medicine here in Daegu. They are very cooperative. For ultra-fast Doppler, we did in Busan universities. Also in Pohang, there is another hospital called Saemyeong Hospital. We are doing breast cancer imaging studies. So we did about 40 patients for breast cancers. So we can write in the paper right now. So maybe we can report as well. So we do have breast cancer, carotid artery, 2 types of foot imaging using the photoacoustic. For UFD, we did kidney disease. Or others, maybe more, but we are discussing about many other hospitals about IRB. IRB is tricky, yeah.
All right, so due to the time limit, so we are closing today's session. And thanks again to Dr. Kim for the great talk. Thank you very
so
much.
much.